woods for roofs and furniture, and this will keep the sequestered CO2. And let's talk about past and current work in estimating carbon sequestration.
Sorry, Dr.
Normally,
Awad, I think I cannot see your slides, so maybe you can just quiz the presentation mode
do you
directly.
see it?
I was still seeing the second slide, but now it's the fourth one, but I didn't see the third one.
Okay.
Yeah,
I
now
don't know
it's
what's
perfect for me.
wrong.
Yeah, thank you.
Here it's fine now.
Yeah,
Yeah,
It's
I
not
think
great.
in the
as
not in
you
the
move
display
from slide
mode,
to
but
slide, Dr.
it's not
Awad,
in the presentation mode. So, but I think it's fine as long as it's fine. It's okay. Do you see the fourth slide now?
Yes, yes.
Okay. Past and current work on estimating carbon sequestration. The conventional way of estimating carbon sequestration used to depend on dividing a study area into plots and taking parameter measurements of the trees that exist in these plots, and then estimating the sequestered carbon in this above ground biomass. This normally takes a long time and requires a large budget to finish this kind of projects. When the advancement in technology was introduced to help in estimating carbon sequestration, airborne radar data, Landsat 8, and ALOS pulsar radar, and MODIS and LiDAR, airborne light detection and ranging, were used in addition to very high resolution satellite images. But these were not completely affordable, and they are very expensive, and sometimes they don't cover all studied area. So we see that we have a variety of spatial resolution and a variety of technologies, but are all these reliable to obtain the needed information for a specific area or for a large area? Sometimes it's not affordable. What kind of or what methods they used in estimating carbon sequestration? That ranged from using conventional machine learning algorithms such as support vector machine, random forest, k-nearest neighbor, and the extreme gradient boosting algorithm. From the literature, we noticed that some used convolutional neural networks to estimate carbon sequestration. At the same time, they compared to SVM and RF, and they ended up finding that convolutional neural network is superior to these conventional machine learning algorithms. Others used very high resolution satellite images by computing the vegetation indices in order to estimate carbon sequestration. So we see that some of these methods were not very successful in giving a reliable results. Why? Because they required large samples. They required they demanded huge computation, and at the same time, they may fall in the local optima, and they converge sometimes very fast, or they may take a long time, such as a support vector machine. So the problems are, they can be summarized as follow. If we were using advanced technologies, LiDAR data is limited by the technology availability cost and the size of the covered area. If we were using very high resolution optical satellites, it has the same problem. It's the same for the radar images. Its availability, it depends on availability and affordability. So they cannot used all the time. Here we are talking about the type of data. And most of the research that were done successfully using the previous conventional machine learning methods, they depended on studying one forest type. We can hardly see that they were successful on different forest types, as I did in this study, or on mixed type of forests. Most of the estimation were conventional ones, such as machine learning, such as SVM, RF, and XGBoost, as I said before. The use of conventional neural network required the computation of very high number. Here we are talking about estimating carbon sequestration quantitatively. So that required the computation of very high number of variables that reach sometimes to 70 variable, 67 variable, depend on the type of research and the area of study. The structure of the deployed CNN is very complex and required a huge number of parameters. And in turn, it was complex and required a long computation time. In general, CNN, convolutional neural network alone, is more effective in detecting patterns than estimating specific information. So the success of CNN is more on detecting pattern than on estimating quantitatively the carbon sequestration. For this reason, I had the following objectives: to create a new lightweight convolutional neural network model called FlexibleNet, to test the new model for estimating carbon sequestration qualitatively, not quantitatively, in peri-urban forest. Peri-urban forest, they are type of complex forests that are mixed with urban settlements. And the estimating is for the above ground biomass. And the second objective is to create a new data set that combine multispectral satellite data. Many issues make the new model better than other lightweight CNN models. The new model's flexibility arises from its ability to adapt to a problem, changes in tuning many parameters, such as the image dimension, resolution, dataset size, and layers, depth, and width. The model uses a few variables. 3 variables represent extracted bands from Sentinel-2 as inputs compared to the huge number of extracted features for other CNN models that estimate carbon sequestration quantitatively. The area of study is located in north of Lebanon, where Lebanon is a country located in the east side of the Mediterranean Sea. The area of study is in the north. Why it was selected? Because it has a variety of forests. As you can see, we have Keris oak, Silicus fir, Lebanon cedar, juniper high, and Brutia pine. So we have different type of forests. Some of them are separated, some of them are mixed. So we have a different type of forest, mixed one or separated one. We did collected data samples from the field, and this represents the different type of forest that exist in the area of study, except Lebanon cedar, because it was prohibited to access the area or to take any samples from there. And at the same time, cedar, Lebanon cedar is the logo of the flag, and it's a national tree. It's kind of a very important type of forest. So we were prohibited from accessing this cedar tree. So we were taking just samples from oak and from pine, from fir, and from juniper. We had 114 samples. For each sample, we took the diameter breast height, and we took the height of each tree. The average samples, the average DBH for oak samples were 119 centimeter, which is the lowest. And the highest DBH was for fir, which is 237 centimeter. And the lowest height was 12 meter for pine, and the highest was 17 for fir. We also collected images from Sentinel-2A and Sentinel-2B for the months of May 2020. The reason for, of course, the image had less than 5% cloud cover. And the reason for selecting the image in May is to have a complete cover of vegetation, especially that we have variety of deciduous and coniferous trees. At that time, we can have all the biomass above the ground or existing biomass above the ground. So we won't have any problem with deciduous trees. The clipped image of the study area has a size of 1115 by 955 pixels, and it consisted of 3 bands, near infrared, red, and green. At the same time, of course, these data were extracted from the Google Earth engine. We extracted the global canopy height for the year 2020 at a resolution of 10 meter. Both Sentinel-2 and canopy high had the same resolution, 10 meter. The methods. First of all, we calculated the quantitative value of sequestered carbon by samples based on the following equations. We had 3 equations, one for computing the cubic meter of volume of biomass, which is equal to the base area of the samples with a unit of meter square, and the height of the sample in meter. So we have the volume in meter cubic, and to compute the base area of the samples or the tree, we calculated it by multiplying by the diameter breast height divided by 2 to the power 2. And we obtain the sequestered carbon tons by hectare using the following equation. Volume of biomass by unit cubic meter multiplied by biomass expansion from this available table from the literature. For the coniferous, it has a different biomass expansion. For the deciduous, we have different biomass expansion. And for the mixed, we have another biomass expansion value. The same apply for the bulk density, which is in tons per meter cubic. The coniferous has a different value. For deciduous, we have a different value, and the same for the mixed. For the carbon content, we see that they have all the same value. For FC is the ratio of the molecule mass of CO2 divided by the molecule mass of the carbon. So we have all the values needed and to obtain the sequestered carbon in tons per hectare. The second step is to create the canopy density layer, and we followed we did the following steps. From Google Earth engine, we extracted the Sentinel-2 image, as I said before, that contains the green, red, near infrared, and the canopy heights. We used the Sentinel-2 image to calculate the advanced vegetation index, the bare soil index, and the canopy shadow index. The equations for computing these are available here. You can see they all use red, near infrared, and the green. So we just needed only 3 bands. These 3 bands have the same resolution, 10 meter. After classifying all these layers into 6 categories, we created the canopy density model. We did the spatial analysis in order to create the canopy density with the classes needed from very low or from no carbon sequestration to the very high carbon sequestration ability. After that, we created a data set or 3 data sets representing different sizes of images. The images of Sentinel-2 divided into 3 different sizes, 32 by 32 by 3. And in addition, it has the canopy density layer for 1 band for each data set with different sizes. We also use these data sets later in the experiments, and we divided them into training, validation, and test categories. We provided these to FlexibleNet model in order to obtain 6 categories representing the carbon sequestration qualitatively. Let's go to the model. Do you see the model clearly here? Hello?
Yes.
Okay.
Yeah.
Okay.
If
The
actually,
model.
Can you just zoom out just a little bit? A little bit of the bottom of the slide is cut off, just a little bit.
Okay. Just let me. Okay. Do you see it well now?
Yes. Yep.
Okay. So the model consists of convolutional neural network, convolutional layers from leaky RELU and from batch normalization layer, from max pool to D, and from fully connected network. And finally, the output classes. As you can see, instead of using RELU, we used leaky RELU in order to, the objective is to slow down the convergence of the model. Okay, so that we don't want to get to the local optima of the solution. So we use this in order, of course, in addition to batch normalization and max pool to D, to reduce the fast conversion of the model. The model consists of layers, which are the number of layers represents the depth of the model. The number of neurons or the number of filters is the width of the model, and the resolution is the height and width of the input image. So we have to tune all these 3 depending on the type of problem we have, depending on the data set size. So initially we start with a filter of 3 by 3. Round n is the closest power of the size of the image for the width and height, or for the width and length, row and column size. The closest power number is used as a value to start the initial filter number. So if n is, let's say, 5, because 32 by 32, then we have 5 over 2 is 3 by 3 filter, initial filter. Then later we continue for each convolution layer. We add different filter size until the final one is 1024. We see that with n greater or equal to 5, 32 by 32. So the next one is 6. So it will be like first it will be like 3 plus 4, 16 by 16 filter, then 32 by 32. And we continue until we reach 1024 as the final filter size. In order to decide the depths of the network, we have n. N is the size of the layer, or the layer or the data set's dimension. So if the dimension is 4, then we, for example, it has to start with at least n equal to 4 or greater than 4. Then in that case, we have 3 over 2 and round to 3, 4 over 2, 2 plus 7. So this is 9 convolutional layers. And we continue until, depending, of course, on the size of the, for example, if the data set is 32 by 32, in that case, we have 5. 5 over 2 is around to 3 plus 5. We have a depth of 8 convolutional layers. If we have, for example, 64, then it has also 8 layers. If we have 128, the data set size, of sub-image size of 128 by 128, in that case, we use 7. 7 is 3.4. We have 7 convolutional layer, and etc. So at the end, if we have a sub-image is greater than 18, then we have only one, which is not possible. These are examples of created flexible net model from different data sets from 32, 64, and 128. We see that each time the complexity is reduced and the number of convolutional layers is reduced too. In order to verify the results, we converted the samples from quantitative carbon sequestration values to a qualitative value. From, as we can see here, the samples are divided according to the estimated sequestered carbon. Those samples with value between 2,000 and 3,400 tons per hectare are given a quality value of very high. For those who are between 1,000 and 2,000 tons per hectare are given a quality value of high. And until the end, which is between 200 and 400, are given a quality value of very low. Okay, so we used these samples to verify the canopy density layer, and we ended up with about 92% accuracy. As you can see, for the very low, we have 23 out of 28 correct. For the low, we have 15 out of 16. For the moderate, we have 21 out of 22 samples. And for the high, 27 out of 29 and 19 out of 19 for very high. The 3 created data sets, as I said before, we had a data set of 32 by 32 sub-images, and it has it's part of canopy density sub-images. And these sub-images represents the qualitative content of carbon sequestration. from dark brown represent very low carbon sequestration to a very high dark green, which represents very high carbon sequestration ability or capability of sequestering carbons in the area. The same applies to data set 64 by 64 and for the data set of 128 by 128. We did some experiments on the flexibility net using these three data sets, and we compared them to a very well-known convolutional neural network, large and light ones. And we can see that the first one was a FlexibleNet with the highest accuracy compared to ResNet 50 with 96.41% as accuracy. And FlexibleNet, I'm talking here about the data set of sub-images with sizes 32 by 32. And FlexibleNet has the lowest number of parameters, 5.52 millions, compared to 31.30 for EfficientNet B5, and followed in efficiency by the MobileNet V3 Large, which has the same timing requirements with FlexibleNet, but it has less accuracy. And in addition, FlexibleNet had the lowest loss value. In the second experiment, we used the data set 64 by 64. We can see also on the graphs how the loss value is progressing with respect to number of epochs. The same apply to the accuracy, and the same we can see for others such as ResNet 50 and EfficientNet B5 and MobileNet V3 and the exception. We can see in the table that the accuracy for FlexibleNet is the highest and has the lowest loss value, and but it has a higher number of parameters compared to MobileNet V3 Large, and at the same time it took more time to converge than MobileNet V3 Large. But this price is paid in order to get higher accuracy, and it's not that big difference compared to the other models such as ResNet 50 or for EfficientNet B5 or for mobile or for exception. The third experiment was conducted on a data set of 128 by 128. And we can see again that FlexibleNet is the highest in accuracy and the lowest in loss value, followed by MobileNet V3 Large. And we can see that MobileNet V3 Large again is better in number of parameters, and it took less time compared to other it took the higher it took a higher time than the FlexibleNet. FlexibleNet here is much better than MobileNet compared to the other experiment, and but the only problem is that MobileNet is less in number of parameters compared to FlexibleNet. Finally, conclusion. There were many advantages of creating the new lightweight convolutional neural network, FlexibleNet. We obtained highest accuracy in qualitatively classifying Sentinel-2 images into different carbon sequestration classes. The FlexibleNet model had the lowest loss value compared to other models. Except for MobileNet V3 Large, the new model used the lowest number of parameters and required the lowest time. Thank you for listening. I'm open for questions.
Well, wonderful. Thank you so much. It was a fantastic presentation. Let's
Thank
just
you.
open
Thank
it
you,
up.
Timos.
Yeah, great. And let's just open it up to any questions on the line.
Hello, Dr. Ward. Thank you so much for this wonderful presentation. So I just wonder, could you explain a little bit about why do you choose CNN, but not other deep learning models? Because seems like for me, like your output is a label for each pixel, right? And CNN is very good at detecting the spatial resolutions with high, the spatial patterns with high spatial resolution. But you mentioned like because high spatial resolution images are not very easily accessible for a large area. So, but you also mentioned that CNN is too complex. So you build a lightweighted CNN. So why not directly use the like pixel-based classification? So you input one pixel and you uh, get a pixel output. So you at that time you can use very simple deep learning models like ANN or
Yeah, yeah,
RN. Yeah. So that's my
yeah.
question.
Thank you. Who was asking the question? Sorry, I didn't hear your name.
Susan.
Okay. Okay, thank you for this good question. I just mentioned before during my presentation that there are some successful CNN methods that used pixel-wise classification in order to estimate the carbon sequestered in each pixel quantitatively. Okay, but these models require the computation of a very high number of variables and features. So if these features are not computed correctly, then the output would be incorrect. At the same time, it requires more time to compute all these variables, in order to extract all these features. So that's the problem. So at the same time, as I said before, CNN is more powerful in detecting patterns than estimating. So not all the problems can be solved, especially for a complex problem such as carbon sequestration. It cannot be solved pixel-wise, although we can try that. We can, for example, use cooperative methods that combine CNN with other conventional machine learning methods to improve the output, to improve the requirements, or to improve such a kind of methods, such a kind of problems of carbon sequestration.
Okay, so does that mean like the spatial texture are also very important for doing this kind of carbon estimation for the image?
Sorry. Yeah, sorry, I didn't hear well
So you
your
think
question.
like
Could you repeat, please?
the texture within the
Yeah,
image is also important
yeah,
because okay, thank you so much.
yeah. That's what I said. We have to compute many features. Probably texture is one of them.
I see. Thank you.
You're welcome.
Any other questions on the line?
Hey there, John. I have a question. And so maybe I missed this. So it looked like you had uh, your model computed at different image sizes. Is there? Do you have a suggestion on which one performed the best comparatively?
Yeah, yeah. Thank you for this question. It's a good one. Yeah, as you can see, let's go back to the results. As you can see from the data set of images of size 32 by 32, I had the best results. Okay, and these results deteriorated later with respect to the number of parameters. As you can see, the number of parameters gets higher in 64 by 64, and the same for 128 by 28. So the best result was with sub-images of 32 by 32. Maybe the smaller sizes provided me with the best result, I guess.
Okay. Yeah, thank you.
Compared to if we compare FlexibleNet to MobileNet version 3 large.
Mm-hmm. Yeah, thank you. No, I mean, it's just interesting, you know, having, I'm sure everyone here it's just dealt with deciding on image chip sizes. So it's always nicer to have
Thank you.
a smaller image. But you know, a lot of the out of the box stuff requires larger images. Yeah, no.
Yeah, I was also limited by the computing resources or facilities that are available. So I wanted to do a larger one, but I was limited with the computation resources.
Yeah,
I wanted to do 512 and the larger, I guess.
oh. Thank you then. I mean, yeah, this is exciting.
It's right. The work I go on to continue that as soon as I have enough resources to conduct more experiments to find out what could be the results. It could probably makes FlexibleNet deteriorate and gets worse. I don't know. I have to try. Nothing is perfect.
Yeah. Thank you.
You're welcome.
Great. Any other questions on the line? I was just going to make a comment and say that, you know, I think this group in particular has explored the mobile net on a few other research projects, partly because of just the lightweight nature. And this is what you've presented is very exciting, I think, to this network, based off of the computational limitations, what you just mentioned. It's so challenging to balance all of that in a cost-effective manner. And seeing sort of this analysis is really interesting for particular use cases. And, you know, it sort of opens up the avenue of different model structures beyond mobile net for something really lightweight and really applied. So very interesting analysis to sort of lay out the building blocks that really sort of build that narrative for employing this. So I know maybe some other folks who we've talked about in the last like 4 or 5 years on using mobile net. Maybe this is a new tool set in the toolbox too. So really exciting.
Thank you very much, Timothy. I'm excited too to participate with you and share this outcome with your group. Thanks very much.
That'd be fantastic. Any other questions on the line? I know we've only got a few more minutes till the top of the hour.
I just wanted to add that the code of this model is available on GitHub. So if anyone is interested, and it's public available with the data sets. I also added the data sets on IEEE datasets platform.
That's wonderful. Yes, and I will. I'll link your paper in the notes as well. I didn't do a good enough job in the lead up. That's my fault. I apologize getting the paper out to everyone in the group.
No, you did the best.
Generally, folks dive in and then they're sort of overwhelmed with all the great details. But I know a lot of this group will take the methodologies going forward. And also, I'll mention that you know, we have about 16 people on the call right now, but our participation, because we're so around the world, we'll get a lot of interest over the next couple of weeks. We'll keep this as a higher priority, because so many folks can't call in at all hours, but the videos of the recording are going to be really impactful for folks addressing some of the carbon sequestration work right now. So again, Dr. Awad, I just want to thank you for, just a fantastic presentation. So much work. I know this is only the tip of the iceberg on how much other research you have going on in sort of the deep learning realm. You're more than welcome to continue to attend these Geo-AI working group. Consider yourself a member. And if you're ever interested in more presentations, do let us know. I just want to thank you again.
Thank you, Timothy, for your generosity and for your help and for your efforts. And I would like to thank all the participants and all who attended this lecture. Many thanks to them and for participating in the discussion. And of course, I will do my best to keep attending this series of lectures.
Wonderful. Yes. Oh, Janet, real quick. I know we just got a minute left. We go to the comments real quick before we just wrap up. Oh, dryland agriculture ecosystem. Thanks for sharing. That's fantastic. Yeah, Janet, let's keep it as a conversation before each of these series. Maybe there's opportunities to collaborate. And Noah mentioned that the Google the GitHub link is broken, I think. So if there's an update, Dr. Awad, do let us know. I think there might
Okay. I'll send it to you by email, and you can share it with others.
That's perfect.
Well,
wonderful. And see you all in 2 weeks, I believe. Let me pull up the notes real quick. I think Chisen Zhang, who had some really great questions as well, is going to be presenting in 2 weeks. Really excited for that. I know you're a relatively newer member, but you've been a very strong member, in the past few months, and love to, give you the space and time for the upcoming talk. So see everyone in 2 weeks.
Thank you. See you.
See you.
Thank you.
Thank you for attending, and see you in the next couple of weeks. Have a great day.
Bye.
Thanks all.
Bye, everyone.
Ciao.